Hello, this is my lab report for Lab 4, Oscillations. The purpose of this lab was to model and analyze the oscillatory motion of a hanging spring mass system using both experimental video data and a computational simulation in VPython. For this, we used Newton's second law, or the momentum principle, to predict motion from forces, as well as the energy principle, which states that the total change in energy, delta E, should remain zero in a closed system where there is no external work being done. Now, the main result of this lab was that my computational model successfully replicated the experimental motion with only small differences due to assumptions, parameter estimates, and the limitations of manual video tracking. For our experimentation, we analyzed a pre-recorded video of an object oscillating on a spring. Using the tracker program, I measured the X and Y position of the object in each frame to track its two-dimensional motion. The origin was defined at the spring's attachment point, and the equilibrium stretch of the spring was about 0.7 meters. The system included the mass of 0.402 kilograms, the spring, and Earth because gravitational potential energy was considered. The surroundings then were just the air, which could cause some small damping effects, but I just ignored those in the computational model. From tracker, I found that the initial position was negative 0.115 in the X and negative 0.652 in the Y meters, and the initial velocity was 0.095 in the X and negative 0.126 in the Y meters per second based on early frame measurements. This is the original video used for my measurements in tracker, showing the oscillatory motion of the hanging mass that moved from side to side and up and down. Here's a screenshot from tracker showing how the points were tracked frame by frame to collect position data for both the X and Y directions that would be used to build my computational model, which I'll show you right now. In VPython, I modeled the system using 3D objects, a blue sphere for the mass and a cyan helix for the spring, all to visualize motion. I used small time steps to make the numerical calculations stable and accurate, and applied the momentum principle at each step to update the velocity and position from the net force, which was the forces of the spring and gravity. Meanwhile, I used the energy principle to verify that delta E total stayed constant and close to zero throughout the simulation. I imported the tracker data into the program for visual comparison and defined my system parameters based on the experimental results. By rearranging the period of oscillation formula as you see here, I derived a value for the spring constant using an estimate of the period from my lab data, finding that Ks equals 6.33 newtons per meter. Then, by taking the equilibrium balance of the gravitational and spring forces, I solved for the relaxed length of the spring and found L0 to be equal to 0.077 meters. The gravitational acceleration g was taken as 9.8 meters per second squared. By doing all of this in my program, I received this as my output. The animation shows the modeled motion as the blue sphere compared directly with the video data in red. Below this is the change in energy versus time graph, which shows the exchange between energies but a constant change in total energy of about zero. The graphs on the right display the X and Y position versus time for both the model in blue and experiment in red. Now, what do these results tell us? Well, overall, the computational model closely follows the same trajectory and shape as the experimental data, though the simulated period is slightly longer. Some likely sources of error include calibration or marking inaccuracies in tracker, small rounding errors when determining parameters, and potential video distortions such as parallax or frame rate inconsistencies. To account for non-ideal spring behavior like air resistance that occurred to some extent in the real-world experimentation, we could add a damping term to the net force, like this linear drag formula, that would gradually reduce amplitude over time to better match reality, especially if the video was a little longer. The energy principle is clearly satisfied since delta E total, the horizontal line in the graph, remained approximately zero, confirming that the model conserves energy as expected in an ideal system. For my analysis, the period of the X position data was about 1.646 seconds, while the Y position data had a slightly shorter period of 1.52 seconds. This difference occurs because the motion combines two independent oscillations, one from the spring stretching vertically and one from the pendulum-like sideways swinging. Each depends on a different value for restoring force, which makes the vertical motion complete its cycles a little faster. Overall, though, the experiment and model agree very closely, proving that even with small imperfections, fundamental physics principles still capture well how oscillations behave in the real world. Thank you for watching.